this episode, we focus on a quiet but powerful force that shapes how AI systems behave over time: feedback loops. A feedback loop is what happens when user interactions influence what the system does next, either directly, like saving preferences, or indirectly, like learning from ratings, logs, or repeated patterns of use. For beginners, it helps to picture feedback loops like a thermostat in a house. When the thermostat senses a temperature and adjusts the heat, the next temperature reading is influenced by that adjustment, and the cycle continues. In AI systems, user inputs and user reactions can act like the thermostat, and the model's future behavior can shift based on that cycle. The security problem is that feedback loops can be exploited, can accidentally reinforce bad behavior, and can cause slow drift toward unsafe outputs, even if the initial design looked safe. Operating feedback loops safely means you keep control over what the system learns, what it remembers, and what it treats as a signal worth reinforcing. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. User inputs are the raw material of most AI systems, and they are also the easiest place for attackers and accidents to introduce risk. People paste things they shouldn't paste, like passwords, customer data, private documents, or internal incident details. People also include hostile or manipulative content, sometimes intentionally and sometimes because the content came from outside sources like emails or web pages. If your system uses feedback, user inputs can become training signals or memory content, which can amplify the damage. For example, if a user pastes a secret into a chat and the system stores that conversation for future improvement, the secret might end up in logs, evaluations, or datasets used by engineers. Even if the model does not learn the secret in a training sense, other humans might see it later, which is still a leak. Safe feedback operation begins with a simple rule: treat user input as untrusted and potentially sensitive, and design processes that prevent it from being reused in unsafe ways. Reinforcement is a broad term for how systems become more likely to repeat behavior that is rewarded. The reward might be explicit, like a thumbs-up rating, or implicit, like users spending more time, clicking more, or using the feature more often. If the system is tuned based on these signals, it can learn that certain kinds of responses are successful. The risk is that what users enjoy or find convenient is not always what is safe or correct. Users often reward confident answers, short answers, and answers that comply with their request, even when those answers are wrong or unsafe. Over time, that can push the system to become more agreeable and less cautious, which increases the chance of policy violations. In security terms, reinforcement can shift the system's behavior toward the path of least resistance. Operating safely means you choose which signals count as rewards and you balance helpful signals with safety signals. A key failure mode here is toxic drift, which is when the system gradually shifts toward harmful content, harmful tone, or harmful behavior because the feedback loop keeps nudging it in that direction. Toxic drift can be obvious, like an increase in hateful language, but it can also be subtle, like becoming more willing to provide risky instructions, more willing to guess about facts, or more likely to repeat sensitive data. Drift is especially likely when the system stores user context and uses it to personalize responses. Personalization can improve user experience, but it can also amplify user biases and unsafe preferences. If a user repeatedly tries to bypass safety rules and the system remembers that pattern as a preference, it may become more permissive with that user. That is a dangerous feedback loop because the most abusive users are also the most persistent. Safe operation requires making sure that abusive behavior does not become a learning signal the system tries to satisfy. Another way drift happens is through contamination of knowledge sources. Many AI deployments use retrieval, where the model pulls in content from documents, tickets, chat transcripts, or knowledge bases. If users can submit content into those sources, then user inputs can become future facts retrieved by the model. If a bad actor can inject misleading or malicious content into a knowledge base, the model may repeat it later with confidence, because it appears to come from an internal source. This creates a feedback loop where misinformation becomes reinforced by being repeated. In security, this resembles poisoning, because the attacker is poisoning the data the system relies on. Operating safely means you protect the integrity of the sources the model can retrieve from. That includes controlling who can add content, reviewing changes, and monitoring for suspicious additions. The model's behavior is only as trustworthy as the information you feed it. Safe feedback operation also depends on clear separation between three concepts: memory, analytics, and training. Memory is when the system retains information to help the user in the future, such as preferences or ongoing context. Analytics is when the system records interactions to measure usage and improve performance, often in aggregate. Training is when interactions influence the model's parameters or fine-tuning data, so the model itself changes. These are different levels of impact and risk. Memory can leak across sessions if isolation is weak. Analytics can create sensitive log stores, and training can embed bad patterns if the data is not carefully controlled. Beginners often assume that any stored data automatically trains the model, which is not always true, but the security risks exist even without training. Safe operation starts by being explicit about which of these you are doing, and by minimizing the most risky forms unless you have strong controls. When feedback is used, it needs filtering and validation, just like any other input. If users can rate outputs, you should ask what a rating means. A thumbs up might mean the answer was correct, or it might mean the answer was fast, or it might mean the answer gave the user what they wanted, even if what they wanted was unsafe. If you treat all positive ratings as equal signals, you can accidentally reward unsafe compliance. A safer approach is to combine feedback with safety auditing, where some interactions are reviewed specifically for policy adherence and data leakage. You can also treat certain categories of interactions as ineligible for training or long-term storage, such as prompts that include sensitive data patterns. The core idea is that feedback is not truth. It is a signal, and signals can be noisy or adversarial. Security-minded operation assumes signals can be manipulated. Another important control for safe feedback loops is rate and scope. If a single user can generate huge amounts of feedback data quickly, they can dominate the signal and steer behavior. This is a form of influence attack, even if the system is not doing full training. For example, a user might spam ratings or repeatedly submit slightly modified prompts to test and push boundaries. Safe operation limits how much influence any one user or small group can have, and it diversifies evaluation across many users and many scenarios. Scope matters too, because you might want to use feedback only to improve user interface elements or prompt templates, rather than changing the model's deeper behavior. Restricting the scope of what feedback can change reduces the risk of drift. Think of it like allowing users to adjust the thermostat within a narrow range, instead of letting them rewrite the wiring of the heating system. You also want monitoring that is specifically designed to detect drift, not just to detect outages. Drift detection might include tracking changes in refusal rates, tracking how often the model mentions sensitive terms, tracking how often users flag outputs as problematic, and tracking how often outputs violate policy. If those metrics move suddenly after a change, you may need to pause updates or roll back. Drift can also happen slowly, which is why trend monitoring matters. A system that becomes 1% more permissive each month may look stable day to day, but it can become dangerous over time. For beginners, the important mindset is that safety is not static. Safety is something you maintain by watching for changes in behavior, especially changes that correlate with feedback processes. Human oversight connects strongly to feedback loops, because the safest feedback processes include human review at the points where the system could learn the wrong lesson. If users can submit free-form feedback text, that text can include sensitive information or malicious instructions. If the system ingests it automatically, you risk storing harmful content and spreading it internally. A safer approach is to filter and sanitize feedback and to have a review process for data that might be used to change the system. Even if you do not plan to train a model, prompt and policy updates based on feedback can change behavior, so they deserve careful review. The goal is not to shut down learning and improvement, but to control it. Improvement that makes the system less safe is not improvement, it is risk. When you put all of this together, Operating feedback loops safely is about preventing two failures at once: being too trusting of user inputs and being too eager to reinforce what users seem to want. Safe systems treat user content as untrusted, protect the integrity of knowledge sources, separate memory from analytics from training, and validate feedback before it influences anything meaningful. They also watch for toxic drift and have the ability to slow down, pause, or roll back changes when behavior shifts. The main beginner lesson is that AI systems are not only deployed, they are operated, and operation includes learning mechanisms whether you intended them or not. If you design feedback loops carefully, you can gain the benefits of improvement while keeping safety boundaries intact. If you ignore feedback loops, the system will still drift, but it will drift under the influence of whoever pushes it hardest, and that is not the direction you want your security posture to go.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.